Hey, logicians, I want to walk you through one of these proofs with quantifiers from section 9D. And these will also involve conditional proof and or indirect proof. So in the textbook, this is from exercise 1, number 17. So here's the problem we're given. And I really recommend that the first thing you do is try to think about what the premises and the conclusion are actually saying. That'll help you to conceptualize it in your mind and give you kind of a rough idea of how you're going to proceed. So as I translate this into English, the first premise is saying the following. If something exists, which is either D or M, then everything is F. The second premise is saying, if something exists which is B, then something exists which is both C and D. And then that conclusion is saying, it's true of everything. If it's B, then it's F. In other words, everything that's B is F. This actually gives me a clue for how I'm going to proceed, because here's what I know. If something is B, then it's also C and D, which means it's D. And if something is D, then something is definitely D or M. And if something is D or M, then everything's F. So I can kind of see the chain of links from something is B to everything's F. And somehow that's approximately what that conclusion is going to give us. But that just gives me a rough and ready roadmap. The complication with this one is that the quantifiers don't range over the entire conditional statement, right? So the antecedent of the conditional statement in premise 1 has got an existential quantifier. The consequent has a universal quantifier. And in premise 2, the antecedent of the conditional statement has got a different quantifier than the consequent. So here's what that means for us. Oftentimes I say, hey, the first thing you do with these quantified problems is you drop out the quantifiers. You instantiate the quantified premises so that you can work with them. You can't really do that quite as easily in this one because, like I said, there's multiple quantifiers in each premise. It's not necessarily the way to go. But we can still apply our general principle of working backwards from the conclusion. Okay. So the conclusion we're trying to get to is a universally quantified statement. For all X, if X is B, then it's F. So I can ask myself, all right, what rule do I know that will give me that? And the answer is easy. Universal generalization will give you that if you've got the premise, if Bx, then Fx. Then you could do universal generalization. So there's a starting point. Now our question is going to be this. What rule do I know that will give me if Bx, then Fx? And nothing simple. I mean, there's a lot of rules that might give you a conditional statement as a conclusion, but the only one that looks like it's going to work in this case is conditional proof. I mean, I don't really have the materials here for a hypothetical syllogism or for material implication or for stuff like that. So it looks like this is going to have to be a conditional proof. So I want to set up an indented proof sequence, which is a conditional proof. So how do I do that? Well, line 3 is going to be the beginning of the indented proof sequence, and the justification is assumption CP. And I always want to start a conditional proof sequence with the antecedent of the conditional statement that I'm trying to prove. In this case, that's Bx. Because down here, I've got if Bx, then Fx. The last line of the indented proof sequence has got to be the consequent of the conditional statement that I'm trying to prove. And then here's what the justification will be. All right, so now here's what I've got to work with. I'm trying to get from premises 1 through 3 to Fx. I'm just going to work backwards in my usual fashion and ask myself the question, all right, where do I see Fx in the premises? And the answer is, well, I see it here up in premise one and the consequent of premise one. I've got this statement, a quantified statement for all x fx. So the question is, let's assume that somehow I'll be able to get for all x fx. We'll figure out how in a second. If I did, what rule would get me from for all x fx to the conclusion, just fx? In other words, how do I drop out that quantifier? And the answer is, that's right, universal instantiation. Okay, so I'm going to assume somehow I'm going to get fx out of premise, for all x fx out of premise one, and then I'm going to do universal instantiation. I'm just working my way up. Okay, how am I going to get, what rule do I know that will get me for all x fx out of premise one? Well, what is this? It's the consequent of a conditional statement. What rule do you know which will give you, as a conclusion, the consequence of a conditional statement? Well, my favorite rule is modus ponens. That'll do that. What other premise are you going to need in order to use that rule? Well, you're going to need the antecedent of the conditional statement, right? That you're trying to get it out of. So here's what you're going to need. Somehow we're going to prove the antecedent of premise one. And then modus ponens will give us for all x fx. All right, you know the next question we're going to ask ourselves. What rule is going to give us for some x, is going to give us, there is something that is either D or M, right? How are we going to prove this antecedent of the conditional? Well, I mean, it's not obvious how you're going to get out of premise two. It's like, where are the pieces? I mean, there is a dx in there, but it's hard to see the bridge. So, but think, what rule will give you existentially quantified statement? That's right. Existential generalization will do it. And what premise would you need to have in order to use existential generalization? How right you are, you're going to need the unquantified version, EX or MX. Okay. What rule do you know? That DX or MX at a disjunction. What rule do you know which will give you, as a conclusion, DX or MX? What rule do you know that will give you as a conclusion a disjunction? Well, sure, there's constructive dilemma, but we don't have the pieces for that. And there's a number of other things too. But the easiest, the first, and my favorite way to get a disjunction is addition. Okay? If I'm going to use addition, what premise am I going to need? I'm going to need the first disjunct. So I'm going to need dx. Okay. So there we are. Now, where am I going to find dx in the remaining premises? Look, I see it up here as part of the consequent of premise two. Okay, how am I going to get it out of there? Well, we're just going to go step by step and assume that somehow I'll be able to get it. So first of all, let's just assume somehow I'm going to be able to get this unquantified version so that I can use simplification to get dx out of cx and dx. All right, well, where am I going to get the unquantified cx and dx from? Obviously, from the quantified version. Well, what rule do I know that's going to give me the unquantified version, the contents of an existentially quantified statement? Yeah, that's right. Existential instantiation. So here's how I'm going to get to that. All right. Well, guess what the question is now? How am I going to get all this? There is some x such as cx and dx. Well, listen, folks, it is the consequence of a conditional statement. What will you know will give you the consequence of a conditional statement? Yes, it's modus ponens. All right, if you want to do modus ponens on premise two, what premise are you going to need? How wise you are, you're going to need the antecedent of that conditional statement for some x dx. And now you just got one rule, one question left. What rule do you know which will give you, as a conclusion, from an unquantified statement dx, which will then give you for some x dx? That is right, friend. It is existential generalization. Remember, generalization rules bring quantifiers back. Instantiation rules drop them out. You've now connected the dots. Everything's done. All you got to do is clean up the numbering like that. Voila. Okay, what was interesting and different about, the quantifiers and all that junk? Well, you had to keep in mind what the quantifiers actually range over and what they don't range over. But besides that, we were just, working backwards up through conditional proof, really in the same way you might have, without quantifiers. So we didn't even have like replacement rules in here. So this was pretty straightforward. That's how you do it.